the Elgamal method. Before we start to look at the method, let's look at some of the basics of logarithms. With a logarithm, g to the power of a to the power of b is equal to g to the power of ab, and g to the power of a times g to the power of b is equal to g to the power of a plus b. To make these discrete, we add a mod p into our operations, and where p is a prime number. This constrains our integers within a finite field between 0 and p minus 1. In the Elgamal method, initially Bob creates his public key by selecting a g value and a prime number, and then selecting a private key of x. He then computes y, which is y is equal to g to the power of x mod p. His public key is then ygp. He will send this to Alice. Alice then creates a message m and selects a random value k. For this, she computes two values a and b. A is equal to g to the power of k, the random value, mod p, and b is equal to y to the power of k times m mod p. Bob then receives these and then uses his private key to decrypt the values and discover the message. The message is b divided by a to the power of x mod p. With the divide by a to the power of x, we basically take the inverse of a to the power of x mod p and then multiply. In the related blog, I've shown the working out to show the proof of why b divided by a to the power of x mod p is equal to m. Elgamal and signatures. With Elgamal signing, Alice has a public key of ygp and a private key of a. She then takes the message m and creates a signature r, s. This signature can then be checked by Bob using Alice's public key. With Elgamal, Alice selects a generator g, a prime number p, and a private key of a. Her public key will then be ygp, and where y is equal to g to the power of a mod p. To sign the message m, we generate a secret random number k, and we make sure that the GCD of k and p minus 1 is equal to 1. Next, we compute r is equal to g to the power of k mod p, and then compute the inverse of k mod p minus 1. The s value becomes k to the minus 1 times the hash of the message minus a times r, and then mod p minus 1. The signature is then r, s. Bob verifies the signature by computing two values. v1 is equal to y to the power of r times r to the power of s mod p, and v2 is equal to g to the power of the hash of the message mod p. If v1 is equal to v2, the signature has been proven. I've given an example of this on the related web page. While Elgamal signing is not used much these days, its method was applied into the digital signature algorithm DSA, and which has been converted into the elliptic curve digital signature algorithm ECDSA. But the major problem with the Elgamal method is the usage of discrete logarithms. These unfortunately require large prime numbers. An improvement is to use elliptic curve methods. So let's look at converting from discrete logs into elliptic curves. In a discrete log, we convert from the form y is equal to g to the power of a mod p into y is equal to a times g. With this, we have a base point of g and then multiply it by a. Look at the difference With the discrete log, we had g, the base, generator base to the power of a mod p, and which was an exponential operation. Now we have a multiply operation with an elliptic curve point. And for the exponential, we have g to the power of a to the power of b, and this is equivalent to a multiplication in elliptic curves, where we have a times b times g. For multiplication, we can have g to the power of a times g to the power of b mod p. That is equal to g to the power of a plus b mod p. In elliptic curve, this becomes a point addition, where we have y is equal to ag plus bg, and that's equal to a plus bg. So the exponential becomes a point multiplication, and the multiply divide becomes an addition or subtraction. So now let's convert our discrete logs and make elliptic curve and make Elgamal into an elliptic curve method. So elliptic curve cryptography methods are everywhere just now. With ECC, we take points on a defined curve, such as curve 25519, and then perform simple addition and subtraction operations. So how can we convert our Elgamal method into ECC? Well, first Alice takes her private key A, which is a random scalar value, and creates a public key AG, and which is a point on the elliptic curve, where G is a base point on the curve. Alice's public key will then be big A is equal to AG. If Bob wants to send Alice an encrypted message M, he creates a random value K and uses her public key, big A, to produce a cipher message of K is equal to small k G. And then the next C is equal to K times big A plus M. And where M is matched to a point on the elliptic curve. Now Alice receives K and C and computes S is equal to little a times K. K is a point on the curve. And then computes the message of M is equal to C minus S. As C and S will be points on the elliptic curve, this will be done through point subtraction. I've given the proof of this in the related blog post. Partial homomorphic encryption with Elgamal. With Elgamal public key encryption, we have a public key of Y, G, and P, and a private key of X. The cipher has two elements, A and B. With this, Bob selects a private key of X and computes Y is equal to G to the power of X mod P for his public key. We can use this for partial homomorphic encryption and where we can multiply the cipher values. With this, we encrypt two integers and then multiply the cipher values and then decrypt. This relates to the operation in discrete logs of g to the power of a times g to the power of b is equal to g to the power of a plus b. We can see by multiplying we are actually adding the values of a and b together. Other applications. There are many other applications of elliptic curve of Elgamal methods, including with authenticated encryption and in zero-knowledge proofs. The days of using discrete logarithms, though, are past, and most implementations now use elliptic curve methods. And so, unlike many others, Taher did not patent his method, and this allowed it to be used freely by others. Thank you.